So this is joint work with Esta, with Philip, and with Rupak. It will appear in CAF 23. Great. So, okay, so maybe some of you know this paper. It was published 4 years ago, and it showed that the spin, which is a model checker which has been around for 40 years, had a mistake. It had a mistake in the partial order reduction heuristic, which is actually the standard one. You are using it all the time. And this bug has been there for probably 20 years, something like that. And nobody knows which effect it has had. Probably, fortunately, not very high, but nobody knows. The error can be traced back to the paper by Doron Pellet, where he described the algorithm for partial order reduction. It contained a mistake. So the point is, what can you try to do about this? And one way of trying to get out of this problem is to use certification. So what is certification? The idea is that you have conceptually at least two agents, a prover and a verifier, right? The prover computes some fact, for example, that the Boolean formula is satisfiable, right? And it wants to prove to verifier that that holds, that the fact that is true. But verifier is only willing to spend polynomial time, right? So then prover sends verifier a certificate. And the certificate is just an object which must have polynomial size in the size of the input, such that verifier can check it in polynomial time. I think it's probably better if I do this here. You are going to see more. So can check it in polynomial time. And what is the classical example of a certificate is just a satisfying assignment, okay? So if I want to convince to you that the formula is satisfiable, I send you an assignment and you check it in polynomial time. Well, but the problem is that, you know, certificates exist for all NP problems by definition, right? That's the definition of NP, that such a certificate exists. But unless, for example, co-NP is equal to NP, you don't have certificates for co-NP or for PSPACE. And in fact, so if I tell you, if you send me a formula asking me whether it is satisfiable or not, and I tell you it is unsatisfiable, then how can I convince you? Well, I can give you, for example, a resolution proof, right? And then you can check the proof in polynomial time, but in polynomial time in the size of the proof, right? And the proof may be, in the worst case, exponentially longer than the formula, right? So, and nobody knows how to obtain a certificate of polynomial size, because otherwise you would be proving that NP is equal to co-NP. So, and the same happens, of course, the same is even worse for PSPACE. And now the problem is, what kind of problem is spin solving? It is solving a PSPACE complete problem. It's getting a Promela program, so a description of a concurrent system and a property, and it's checking, you know, and we know that that problem is PSPACE complete. But, you know, 30 years ago, this theorem was proved. IP equals PSPACE. Okay, this was proved by Lund. First, there are two papers. In the end, it was proved by Shamir, but working on previous work by Lund et al. And what is IP? IP is the class of decision problems with interactive proof systems. And you should read this maybe as interactive certification systems. I think it's would be a better name. So, and what is that? Let me explain what is that. Because, you know, the idea is that when we do certification, the standard notion of certification, that is a one-round thing. I send you a certificate and you check it. So it's like there's one round of communication. The idea is that in an interactive proof system, there can be many rounds of communication. So we have a prover and a verifier. The verifier is only willing to invest polynomial time. And, you know, the verifier, but the important point is now we are going to allow the verifier to generate random numbers. So the verifier can generate random numbers, right? Okay, this is a first difference with the scheme that we saw a minute ago. And now what happens? So verifier asks a question to prover, can you tell me whether this quantified Boolean formula is true, right? And verifier or prover says, yeah, it's true. Okay, but how can verifier convince himself or herself of this fact, right? So actually the idea is that verifier is going to engage in a protocol, in a communication protocol with prover, which is going to have a number of rounds. So verifier sends a challenge to prover for which it may have generated some random number, okay? And then prover answers, and then verifier sends another challenge, and prover answers. And this goes on until the end of the protocol, and then the protocol must be designed. You say that the problem has an interactive proof system if there exists such a protocol in a way that verifier can only be fooled by prover with probability 1 divided by 2 to the O of n, where n is the size of the formula set. Okay? So, and notice that we have now probabilities in place because of this ability of prover, of verifier to generate random numbers. So nobody knows how to do this without this caveat that there is a small probability that verifier is fooled, but in practice, that's not going to be much of a problem. Okay, so now the idea is that in order to prove that PSPACE is contained in IP, which is the interesting part of the proof, right? We want to show that for every PSPACE problem, there exists such a protocol. And what Javier does is to give a proof system for QBF, right? And now I have to tell you a little bit about what he does. But for my purposes, it's better if instead of taking QBF, we take a slightly different problem, actually a more general problem. So, and this is, first, let me try to describe the problem, right? The problem, let's call it extended Boolean circuits. So first, what is a extended Boolean circuit? So, you know, it is a diagram like this one, where the nodes, the leaves, actually, there are going to be leaves. It's going to be a cyclic diagram, and the leaves are going to be labeled with variables, and then you can have Boolean operators in the nodes. But you can also have these nodes, which are partial evaluation nodes. And to tell you what that means, let me just give you an example. So the idea is that an extended Boolean circuit is going to be a compact representation of a Boolean formula, right? And which is the Boolean formula? Well, you can pretty much imagine how it is built, which is the Boolean. We are going to associate Boolean formulas to all nodes going bottom up, right? So first, which is the Boolean formula we associate to the nodes labeled with variables? Well, the variable itself. And then to that, we associate the OR, and there we associate the AND of the two children, right? And now what do we do when we have one of these partial evaluation nodes? Well, it's what you would imagine, right? We set Y to true, okay? And then you get that formula. And on the other side, you get that formula, and at the top, you get the AND of the two formulas, okay? Good, and then of course, if you apply the standard simplifications, you will get that that the formula represented by this particular extended Boolean circuit is just X. Well, so the problem I want to consider is this one. Given an extended Boolean circuit, something like this, is the formula associated to it satisfiable? Okay, and this problem is actually PSPACE complete. Why is that? Well, it's because the circuit is a very compact representation of the formula. So the formula can be exponentially larger than the circuit. But more specifically, with the help of these partial evaluation nodes, you can very easily simulate quantifiers. So if you want to say, so the formula that exists an X such that phi, the quantified Boolean formula that exists an X such that phi, is equivalent to taking the OR of partially evaluating with X equal to true and X equal to false. So this means that now if you want to construct a Boolean circuit for some quantified Boolean formula, well, for example, if your Boolean formula starts with for all X there exists a Y, then your circuit is going to start like this, right? This is going to be the for all X, and this is going to be the there exists a Y. So the idea is that the circuit is going to have actually linear size in the size of the formula. Sorry? Sorry? It should be Y. Yeah, sorry, there is a typo there. But yeah, thank you. Okay, good. So now, which is the first step in Javiers' proof? And this is actually probably the key idea. The idea is to assign to each node of a circuit a polynomial. Okay, not just a formula, but a polynomial. And how do we do it? Well, which are the polynomials that we assign to the leaves? What you would expect, right? Now, what is the polynomial that you assign to an OR node? So there is more than one way of doing this, but here we are going to do it like this. We assign to it the sum of the polynomials of the children minus the product of the polynomials assigned to the children. Okay, good. And then what is the polynomial you assign to an ant? It is the product of the polynomials you assign to the children. Okay, so and when you is going to be this polynomial. And then what is the polynomial you assign to a partial evaluation node? Well, you just set the variable to 0 or to 1 accordingly. Okay, so that's what the polynomial you get up there on the left. So which you can simplify to x, and that's the one you obtain on the right is x squared. Yeah, because you assign now 0 to y. So right, if this second part goes away. And then at the top, you are going to have the product of these two polynomials, and you get x cubed. So notice that it's not the same as the Boolean formula, right? The Boolean formula was x, now the polynomial is x cubed. Good. And these are all binary polynomials. You can very easily prove that. And what do I mean by a binary polynomial? A polynomial such that when you assign to it binary inputs, so when you set all the variables to 0 or 1, in any way, you always obtain as result 0 or 1. That's what I call a binary polynomial. Good. So, okay, so this is our assignment of polynomials. And now what you can easily prove is this. This is a very trivial proof. The Boolean circle is unsatisfiable, and I mean the formula that it represents is unsatisfiable if and only if the binary polynomial is the 0 polynomial, is the identically 0 polynomial. Good, so therefore, what we obtain is that deciding that is also PSPACE complete problem, okay? And you can imagine that the problem is going to be that, I mean, why computing these polynomials is not easy? Well, because they can get very large, okay? So you will need exponential time to compute the polynomials in general. Good, so now let me tell you, try to present to you an interactive proof system for this problem, okay? And I'm going to first present you a version which is not yet correct, but which helps to understand the idea. So the idea is the following. So the verifier tells prover, well, please give me the polynomial of this node, okay? And prover answers, the polynomial is x to the cube, which with that, prover is telling to verifier the formula is not unsatisfiable, because otherwise I would have told you 0, okay? So it is answering also the problem. So, but then of course the idea is verifier, why should I believe this, right? And then the first idea is verifier says, okay, let me take a random number. For example, 31. And now you probably immediately ask, but what do you mean by a random number? I mean, you cannot, how do you choose the number? Well, actually, what this means is I'm going to take a sufficiently large finite field. In the tool, for example, we take 2 to the 61 minus 1. I mean, the finite field generated by the prime 2 to the 61 minus 1. Okay, it has 2 to the 61 minus 1 elements, right? And then you choose the element uniformly at random. Okay, good. And then the idea is, this is the second crucial idea. If the polynomial is not x to the cube, so if the real polynomial is something else and prover is trying to fool me, right, then it is very unlikely that that polynomial on 31, it gives me 31 to the cube. And probably many of you know this. This is what is called the Schwarz-Zippel lemma, which is a very simple result, which is actually immediate consequence of the fundamental theorem of algebra, let's say, right? The idea that if the polynomial has degree 4, then it's going to have at most 4 solutions, 4 zeros, right? But since you can evaluate it on 2 to the 61 minus 1 different elements, the probability that you hit one of those is very small. So this is essentially the idea. This is the formal statement, and which you don't have time to understand now, but essentially what this is telling you when you apply it is that if the polynomial is not x cubed, sorry, then the probability that that polynomial evaluated on 31 gives me the same result as x cubed is at most that number, okay? And that number is very small. Good, so what then verifier says is, okay, let's see if PA of 31 is that number or not. That's 31 to the cube, right? So then what verifier says is, okay, well, let's look at the circuit. This is an AND node. So PA of 31 must be equal to the product of PB of 31 and PC of 31, right? Okay, so then prover, please give me PB of 31 and PC of 31. And let's see if what you give me when I multiply those two numbers gives me this, right? Let's see if you are able to be consistent with your previous statements. So prover answers, well, PB of 31 is 31, and PC of 31 is 31 squared. Okay, good. Then verifier says, okay, this checks out. When I compute the product, indeed, I get what I should get. So now the idea is that everything relies on whether you are telling me the truth about PB and PC. And now we can iterate, right? Let's see if PB of 31 is true. And later we will check PC of 31. So let's see if PB of 31 is true. And then let's look at the circuit. PB of 31, you know, the polynomial here is a polynomial on two different variables, X and Y, right? And you obtain the polynomial here by evaluating Y to 1. So the polynomial PB of 31 should be equal to PD of 31, 1. Okay, so prover what prover says is, give me PD of 31y. Give me this polynomial, right? Which is with one variable 1. It is actually a polynomial with one variable, one single variable. So prover answers with this. And now verifier checks, okay, fine, yes, indeed, if I replace y with 1, then indeed I'm going to get the right number, right? So good, it checks out. Checks out. And now the idea is, okay, but is this the right polynomial, or is verifier trying to fool me, right? And then what verifier says is, well, let's take another random number. Now let's say 17, okay? And let's apply the same principle. If this polynomial would not be the right one, then it would be very unlikely that when I evaluate it on 17 for y, I get this result, right? So now let's see if this is true, and then it goes on. And the good thing is that when we reach the bottom, when we reach here, then prover will have claimed something like PF of 31 is 31. But now verifier does not need prover anymore. We are down to a polynomial which verifier can compute by himself or herself. And then the idea is that at that point, right, if verifier has been trying, if prover has been trying to fool verifier, at the latest at that point, everything will break down. Now, prover will not be able to fool verifier anymore, or only with a very small probability. So that's the basic idea of the algorithm. But, you know, as I told you, this one is not yet correct. And why? Well, the reason is that in this protocol I have presented to you, verifier still needs exponential time. And why is that? Well, think, for example, of this tree. You can see that the degree of the polynomial is going to grow, may grow exponentially, right? And therefore, for example, when verifier asks, please give me this polynomial on X, it may get as answer a polynomial with an exponential exponent, right? And then it can be, the polynomial may be exponential itself, because you may have all the other exponents going back to 1, right? So this doesn't work really. But this is the trick of Shamir. This is actually mostly the contribution of Shamir. The idea is that you can use this degree reduction trick. So imagine that you have a node in your circuit, and that node has associated a polynomial over variables x1 to xn, right? Which we have defined in the way we have defined them before. So the idea is that we are going to introduce extra nodes in the circuit called degree reduction nodes. And what are these degree reduction nodes doing? They are reducing the degrees of the corresponding variable. So the idea is the following. Imagine that this polynomial would be something like this, right? Imagine this polynomial is this one. So then we have this polynomial here. And now which is the polynomial we assign to the next node? It is the result of reducing the degree of all x1s to 1. Okay, so instead of x1 to the cube, now you have x1. Instead of x1 to the square in the next one, you have x1. And notice that this doesn't change the value of the polynomial for binary inputs. As long as you keep 0 and 1, everything is fine. It will change the value of the other inputs, right, for other inputs, but not for 0 and 1. So basically, the intuition is that the result that the formula is unsatisfiable if and only if the polynomial is identically 0 is going to remain true. Okay? Good. So now you you reduce the degree of x2, and then you keep doing that until you reduce the degree of xn. And at the end, of course, you have now only a polynomial where all powers are just 1. All exponents are 1. Okay? So this is what we call a multilinear polynomial, right? Polynomial, multivariate polynomial where all variables have exponent 1. Well, or 0, if you want, right? It could be in a monomial, you don't have to have all variables. So you still keep the property that the extended Boolean circuit is unsatisfiable if and only if its associated polynomial after degree reduction is 0. Now, the point is that when prover and verifier execute the protocol, they don't execute it anymore on this tree, or on this on this circuit. They execute it on this circuit with the degree reduction nodes interleave there, right? So the idea is that whenever a polynomial might not be multilinear, then you introduce degree reduction nodes that make it multilinear. Now it could stop, because of this and, it could stop being multilinear. So then you introduce degree reduction nodes to make it multilinear. You always bring it back to multilinear by adding these intermediate nodes, right? And now the interesting thing is, all exponents that you are going to get throughout in all nodes, when you construct the polynomials in this way, all exponents are going to be at most 2. Notice that the polynomials may still be exponential, because if you have n variables, then the number of monomials that you can have on n variables is still exponential. But you no longer have the problem with the degrees, right? And now the idea is that, remember that what we did was to, when we were, when prover and verifier were running the protocol, they were going top down, right? So verifier was asking the question about the top node, and then it was saying, okay, let's see if I believe you. It was going down, and so on. So now the same protocol works. I would have to tell you what must verifier do in the degree reduction nodes, but I will skip that. It's really very simple. You could get it in 1 minute, right? So the idea is that now, since the polynomials have constant degree, and verifier is always asking only for polynomials in 1 variable, when you apply the algorithm, the challenge is that verifier is sending to prover is, give me this polynomial on this unique variable, right? Then verifier is only going to invest polynomial time. Good. So I spent all this time just to tell you this, to give you an idea of how this works, right? So this is all 30 years old. But now the question that, yeah, sure. Sorry? Doesn't change. I mean, it changes only a little bit because you have more nodes, but the number of nodes only grows by a constant. So it's not a problem. So basically, the probability is essentially the number of nodes divided by the number of elements in the field, more roughly speaking. Good. So now the question is, well, this was all done 30 years ago. Why don't we have it in tools? Why are not, for example, why don't we have a library, self-certifying library for this problem? And the reason is, or why don't we have certified model checkers, or why don't we have QBF solvers yet applying these techniques? And the reason is, or at least what we think is the reason, is that when you look at this proof, all these guys wanted to prove, they were complexity theorists, they just wanted to prove the result. And for that, in order to prove the result, it is completely irrelevant how much time prover has to invest. And then they were given an algorithm for prover without caring at all whether that algorithm is efficient or not, right? And in fact, if you look at it, they even present it in the proof as an algorithm where prover, in the best case, needs exponential time. So that's, of course, like asking prover to compute the truth table of the formula or something. That's very bad. And that's, we think, is the reason why this wasn't used at all. So the idea is now, why don't we take something which it is appreciated by the community as a reasonable way of solving this problem, and why don't we try to give an interactive proof system where the prover can apply this, and where, after the prover has computed, it doesn't have to spend much more time in order to do the certification. So actually, the goal is that prover does its thing using, for example, we are going to do it here with BDDs. Prover does its thing using BDDs, and then the certification is only going to take constant more time than the time needed to produce the BDDs. Okay, so this is going to be also a good deal for prover, not only for verify. That's the idea. Okay, so now let me try to sketch how this thing works. How do you construct an interactive proof system based on BDDs? Well, the first thing is, how do you solve the problem, the problem whether the formula is unsatisfiable or not? How do you solve it using BDDs? Well, you start at the bottom and you construct the formulas bottom up, but instead of the formulas, what you construct is a BDD for the formula, right? So for example, when you are, so we represent the formulas as BDDs. So for example, instead of constructing this formula here, you don't construct the prover does not construct that formula, it constructs that BDD. And prover moves up, right? Constructing BDDs. Good. So then, what's going to happen is that prover will, in principle, will have to construct all these polynomials, right? It will have to construct all these polynomials for these nodes because verifier is going to ask questions about them. But what prover has is just a bunch of BDDs it has constructed, right? So what prover is going to do is to also use BDDs, actually something called extended BDDs, to represent the polynomials. Okay? And how can you use BDDs to represent polynomials? Well, you all know how to construct BDDs, right? So you start with two nodes, 1 and 0, and then, for example, you can add this new node, which the idea is with 1 goes to this node, with 0 goes to that node. So now these correspond to the formulas true and false, and that if those nodes correspond to two formulas, phi1 and phi0, that node corresponds to the formula x and phi1, or not x and phi0. You all know that about BDDs, right? Good. So then, if we want to see BDDs as polynomials, what do? You assign to these two BDDs the polynomials which are identically 1 or 0. And if these are the polynomials assigned to those two nodes, you assign to this node this polynomial, x times p1 plus 1 minus x times p0. And in this way, every polynomial, every BDD is representing not only a formula, but also a polynomial. Okay? Good. So how do you assign polynomials here? For example, this will be the polynomials for those two nodes. That's the polynomial assigned to this node, which is 1 minus z. That's the polynomial assigned to the other node, which is z. That's the polynomial assigned to that node, 1 plus z minus 2 yz. And that's the polynomial assigned to the top node, which is this one. Okay, good. So what you can easily see is that the BDDs which polynomials can you represent with BDDs? Exactly the binary multilinear polynomials. Okay, this is a little theorem, not difficult to show. So remember, binary means if the inputs are binary numbers, the output is binary, and multilinear means all powers are 0 or 1. So for example, x squared y is binary, but it's not multilinear. 2xy is multilinear, but not binary. And this one is both binary and multilinear. Those are examples. And now, what is the first thing you can prove? Well, remember that all polynomials we were obtaining were binary, right? When we were constructing the polynomials, all of them were binary. This means they can all be represented by BDDs. And now, those ones marked in green, they are all multilinear. Because remember that the degree reduction was designed to bring them back to multilinear. So now it turns out that these ones are, when I said I said something wrong. That all polynomials are binary doesn't yet mean that they are representable by BDDs. For BDDs, they also have to be multilinear. But all these ones, they were not only binary, they are also multilinear. So these ones can be represented by BDDs. The ones at these nodes, right? And now what is the first theorem? The first theorem is what are those BDDs? Exactly the ones that prover computed anyway. Okay, so prover doesn't have to do anything to compute those polynomials. It has already computed them. So when verifier asks about them, prover just gives the polynomials it has already computed. Okay, but we are not yet done, because those ones that correspond to degree reduction, they are not multilinear. They can have squares around there, right? And what can we do about that? And this was essentially the main problem, right? What can we do about that? And how much time I have? Probably minus 5 minutes or so. Nobody knows? Then I continue. So I continue until you tell me, right? Because then I can do this faster or slower, or probably I have to do it very fast. That's always the standard answer, right? What? I have 20 minutes? Wow, amazing. Okay, then I can take my time. Any questions? Did you get it so far? Good. So, yeah, okay. So actually, you see, so let's, oh, why is this? For some reason, there is a technical problem there. But anyway, then let me go through this more. Let me let you savor this, right? So remember, the idea is that in order to solve the problem, prover will have to start computing BDDs for all these nodes. In fact, it only needs to compute BDDs for the ones in green, right? Good. And then later on, verifier is going to start asking challenges from the top, right? But not about those BDDs. It's going to start asking challenges about the polynomials. But then the theorem tells prover, you don't have to worry. You already have the polynomials, right? But the problem is what happens with the other nodes. For those, when verifier asks questions, prover doesn't know the polynomials yet. So what can we do? We are going to do the following. So remember how probably at some point, I hope you have heard about BDDs or learned a little bit how to construct BDDs. In particular, if you have a BDD node here, U, imagine it is this one, and this is the BDD for that node, right? And imagine that you have another BDD node, V, for this is this node, and imagine it is there. Now the question is, how do you compute a BDD node for this here, right? So here you have to think about, so actually you have to think, I think I didn't say it correctly. You have to think about this as a fragment of the extended Boolean circuit, right? In the extended Boolean circuit, I have two nodes, and then I have an OR node. And my task now is to compute BDD nodes for all these nodes. So assuming that I have computed a BDD node for this node in the extended Boolean circuit, and assuming I have computed a BDD node for this node. The question is, which is the BDD node that I associate to this node in the extended Boolean circuit, right? In this way, if I have a Boolean circuit in front of me, I can assign BDD nodes to all the nodes, right? Well, I hope you remember that this is going to be the solution, but I hope you remember how to compute it. There is an algorithm which, given two BDD nodes, computes a BDD node for the OR, okay? And if you remember, the algorithm works recursively, okay? It goes from top to bottom. But let's, before going into that, so the idea is that, when I take now this fragment of the Boolean circuit with the degree reduction nodes, right? The idea is that I already know which is the BDD node I need to know this polynomial. I know the BDD node for this polynomial because they are the same as here. And I know the BDD node for that polynomial. The problem is I don't know which are the BDD nodes I need for the two in the middle. Okay? So, and for that, let's see how to compute them. Well, if I want to compute the OR of these two nodes, of U and V, right, I'm going to do that recursively, if you remember. The idea is I compute the OR of the one children, in this case of this node and that node, and then I compute also the OR of the 0 children, okay? In that case, that node, and the other one would be the 0 node. And when I have computed those nodes recursively, then the node I need is the result is this one, okay? The one which has those two nodes as 1 or 0 children. Actually, in the case in which these two results are the same, then it will not be exactly like that, but forget about that for a moment, okay? So, and then I am going to compute those things recursively, right? Now, in order to compute which is this node, I will take the 0 children and the 1 children, and then I will compute results and so on. And in fact, that will be the way of obtaining this result. Good, so now go back. Which are the polynomials for these two intermediate nodes? So what we show is the following. So let's assign also a polynomial to that node. In the same way, right? We take the polynomials for these two nodes, for U and V, and then we apply the corresponding operation for OR, right? And this gives us a polynomial. In fact, we are going to obtain the polynomial of U plus the polynomial of V minus the product. That's the definition. And it's actually going to be this polynomial. Good. This is the result. That polynomial is that one. Okay, so what the idea is that these two polynomials that I need, I am going to obtain them as intermediate results along the computation of the BDD for the OR of U and V. And this is something that Prover also had to do anyway. In order to compute the BDDs, Prover had to apply this algorithm. So when Prover was just trying to answer the question, right, without worrying about what's going to happen later when you have to verify, when it's going to interact with the verifier, Prover already computed those things as well as intermediate results. What Prover has to do is keep not only the results for the nodes in the extended Boolean circuit, but also keep the intermediate results. And with that, it has BDDs for all polynomials it is going to need. Okay, so actually, we call this diagram an extended BDD. That's why we call it extended BDD, because we are also going to have these nodes. And what we do is assign polynomials to them. And during the computation of where you are just trying to see whether the formula is unsatisfiable, you are just, what you do is you just store these intermediate results. And then, you are going to recurse, and then again, you are going to assign a polynomial to that node, and that's going to be the polynomial that you need there. So, when you are computing, if you go back, right, when you are trying, when this is a task that Prover has to do anyway, compute the node for that OR, and it's going to do it recursively, but it's going to store the polynomials, or it's going to store the intermediate results, sorry, not the polynomials, and those intermediate results are encoding the polynomials it needs. Good. So we have then EBDDs for P1 and P2, which are computed, right? While computing the BDD W here. And this means really there is zero overhead. The prover is going to doesn't have to do anything new, apart from, and this is in practice non-trivial matter that we are working on, apart from storing intermediate results, which of course can be a memory overhead, not a time overhead, but it can be a memory overhead. Good. So later, maybe just a quick thing. So remember that what what verifier is going to do is send prover challenges, right? And the challenges are always of the form, evaluate this polynomial. Sometimes also give me this polynomial almost evaluated in all variables, but this one. But let's forget about that for a moment. Basically, it's evaluate this polynomial. So the idea is that you have to evaluate the polynomial, prover has to evaluate the polynomial, but now the polynomials are represented as BDDs, okay? So what prover needs is an algorithm that evaluates the polynomial without constructing it explicitly, only directly from the BDD representation, okay? But that's not very difficult, right? So this is the polynomial that is represented by this BDD, if you apply the rules, which is the semantics of a BDD as polynomial, right? So now imagine that verifier says, I want the value of this polynomial at 17, 32, and 6. Please give it to me. Okay, x is 17, y is 32, z is 6. Well, what prover is going to do is, well, it knows that the value of this polynomial on this input is 0, and this is 1, because that's always the case, right? And now for z, well, it's going to plug in the value for 6. The value for z, it is 6. And prover knows which is the polynomial this one stands for. So actually, it's going to apply the operations, and it's going to get -5 as result. And then this is going to continue. There, it will obtain 6. And then there, it will plug now the value of y, and it will obtain -352. And then it will go up to the root, and it will get the final result, -6080. Prover never has to construct the polynomial, okay? It works with this compressed representation of the polynomials. And thus, this has linear time in the size of the BDD. Good. So the summary is, that given, forget this close, that's a typo, given a, so given an extended Boolean circuit, the question of deciding whether its binary polynomial is, I thought I had corrected this. The question whether its binary polynomial is 0, which is the question whether the formula is unsatisfiable, right? That question can now be solved. Right, I had corrected it here, but not there. Good, okay, so yeah. So this is let's forget about the previous one. Given an extended Boolean circuit, the question whether its binary polynomial is identically 0, right, can be answered without overhead. So the theorem is this one. If solving an instance of this problem, right, using BDDs takes time t, then solving plus IP certification using EBDDs takes time O of t. Right now, our constant here is around 4. Okay, that's what we get. Good, and this is implemented, up and running, and in fact, it's available. So you can, the tool is called Blick. And so it is in GitLab. And so if you look for it, you should be able to find it and run it. So we got the badge that is reusable yesterday, so it should be fine. I guess the badge from CAF. And here are some random experiments. But the important thing that I want to, so here, for example, you have the time that prover invests in total. This is the time that prover invests in evaluating the polynomials. This is the overhead. The overhead is evaluating the polynomials on the BDDs, because, you know, constructing the BDDs, that is what the prover has to do anyway. Okay, so this is the overhead. And you have here the time that verifier has to invest, and as you can see, it's always negligible. So for verifier, this is nothing. But notice that we care not only about the time for verifier, we also care about the time for prover, because actually for us, prover and verifier are in the same program. What we want is to have a certifying library. So the idea that whenever you do an operation, whenever you execute, right, you certify as well. You have to trust, of course, the program, the verifier, but that's a very tiny program, which is just basically just doing a couple of polynomial operations on polynomials, right? So, but you can see that, so we care about this, but you can see that it is actually very, very reasonable. And then, you know, our BDD solver is competitive with BDD solvers around. So as long as you are interested in solving it with BDDs, and there are some tools around, then the certification doesn't involve anything. So that brings me to the end, right? So basically what I want to convey to you is it has taken 30 years to notice this, right? But IP equals PSPACE is not only a theoretical result, okay? Now, what we have shown is that IP systems are compatible with BDDs. And now, of course, the questions immediately shows up, but what if I am using resolution to solve the problem? Or what if I am using these other things, okay? There are solvers based on other techniques. And then we are working on that. It is compatible with certain very restricted forms of resolution. We conjecture it will not be compatible with arbitrary resolution, but probably there is something in between, which is very interesting. But we will see. Time will tell. And what whenever the idea of trying to apply IP equals PSPACE, do I still have a minute? Yeah. Good. The idea of applying IP equals PSPACE, I had it 10 years ago or so, and I am sure that many people in this audience have also had it. In fact, I have talked to some people about this. Well, wouldn't it be possible to apply this for certification? We are solving PSPACE complete problems, so it is the perfect application, right? Our standard problem is a PSPACE complete problem. And everybody was saying, yeah, actually, I also thought about that. So I think many people have had that idea. That's not, and the problem is that I didn't have a clue how to proceed. But now, and mostly thanks to Philip Cerna, who is a very bright PhD student, one of the co-authors of the paper, right? So now we finally have a first step. And I hope that there will be more. And that's it. Thank you very much.
Since these polynomials, they are thought to be evaluated in Boolean value, then can you consider that if two polynomials evaluate the same on Boolean values and differ on other values, it's not they are equivalent, a bit like to suggest with
that's
reduction, and then the prover could only. What happens if the prover only asks
you mean what happens if verifier only asks challenges instead of picking random numbers over this field? What happens if it's only allowed to pick 0 or 1? Well, then prover can fool you. I mean, this is the key idea. The key idea is that you can. The idea is that I convince myself that you have the right polynomial by asking you to evaluate the polynomial on one single point. If I cannot choose among a very large intuition, if I cannot choose out of a very large pool of possible inputs, if you know that I will only ask you about 0 or 1, then you can fool me.
Okay.
So this is, and of course, that's the credit to that idea goes to the complexity theory guys who found this very beautiful extension of consider, arithmetize, which basically, if you are only thinking about binary inputs, is just another representation of the formula. But now you can do something else, which is evaluate on many more values. Yeah.
Started with this mistake on partial order reduction. So how you relate that
right?
To that?
So I am not able to repair a spin, right? But definitely, what is within reach is to have a BDD-based model checker, new SMB, which certifies its outputs. That's perfectly possible because actually, what the new SMB is going to do is going to, in order to verify a particular problem, you can imagine that what it does is to construct an extended Boolean circuit and evaluate it, right? So, of course, which is the circuit depends on the system and the formula you want. But essentially, it's going to be a very large circuit, and now you can do the certification. So that's perfectly within reach. Of course, whether it will be efficient enough, whether people will buy it, and so, I don't know. But it is within reach. And in fact, we are moving towards that. For example, right now, the fact that you have to store the intermediate results can be a big problem. And then something which is very interesting is, when I implement a tool, the tool may have bugs, but the tool is not going to be malicious. The tool is not purposely intending to fool me, right? And then the question is whether one can formalize that assumption in order to have weaker warranties, but which are good enough for certification and which allow you to not to have to store the intermediate results. And I think that's common. Yeah.
I have a question about those intermediate nodes for, let's say, the exponent reduction, right? So it seems that lots of your technical trouble was to compute the polynomials in those nodes where they are not what is the term?
They are not multilinear, yes.
So in the in the certification process, wouldn't it be possible to jump over those nodes somehow, right? So that prover doesn't actually have to answer any questions about them. It's just telling verifier, sorry, I can't answer here. Please go one further.
The problem is that verifier, if you want to obtain the probability, the high probability, verifier has to check at every point that is not being fooled.
Okay, so jumping over is not
jumping
possible.
over would not work.
Okay, thank you.
Would not work. Basically, it amounts to, well, I don't even know if I would be able to explain it. So Philip would probably do a much better work, much better job than me. Yeah.
Also on these additional polynomials that you have to care about, is it worth not computing or not remembering them, but computing them only on the fly? Since they are kind of local. You have this bunch of deltas, say 5 or 7 in a row, that all
it is. I think it is more or less the same question. So you cannot, for example, do it in one go. Okay.
No, that's clear.
Also because you have also to relate that to BDD operations. And you can do it for one variable at a time. And if you do them in one go, that would not work. You mean that computing them on the fly without remembering them? No. So the problem is that verifier is going to ask questions about all of them. And the problem is always that when you construct them bottom up, but the protocol rounds top down. So that's why you have to store them, right?
So I should be more precise. Yeah. What you said in passing was, it's not really a time problem there, but a memory problem.
Yes.
But in any, whenever you exchange this information, then the protocol goes down only one path along the OBDD.
That is correct.
So essentially, you waste a lot of money, of memory.
Money too, yeah.
Money too, yes, indeed. But who cares? It's official. It's public money. But But
okay,
most of the memory is
Yeah.
not really used in the verification. Let's put it that way.
Well, okay, so let's see.
What's
The
that?
problem is, okay, you could think about, well, let's start from the certification anyway, and then let's compute the polynomials or the BDDs for the polynomials only as I need them,
In a sense.
right? But imagine you start at the top, and then you say, okay, so I'm going to have to construct BDDs for the two children in the extended Boolean circuit, right? But now, how do you compute the BDD for that?
No,
The problem is you have to go all the way around, all the
No,
way
I recall
to the
those.
bottom.
I recall the main ones, the obvious ones that you already have as BDDs,
Okay.
and only if the verifier asks me to go along this delta path.
No, the verifier is going to go through all delta paths. So it's going to go through all the. Maybe let's take that offline. I think it's yeah.
Now that I have the microphone, I try to ask.
I mean, it would be an interesting point, right? I mean, that is definitely the question now is how to avoid redoing things or how to avoid having to store things. I think that one you are suggesting probably doesn't work, but let's discuss it offline. Yeah.
But sorry, I still have the microphone and I use it. Just a second. Is there a formal meaning to your second bullet point that it is compatible, or more interesting, that is not compatible with some other systems?
Well, okay, the formal meaning is the theorem, right? The formal meaning of being compatible is, can you obtain a theorem of this form? So replace now BDDs for whatever you want, right? And the question is whether, given that solving the instance with this technique takes time t, whether you can find a protocol such that the whole protocol, right, runs in time O of t. For example, that would not be the case, right, if you would be solving using resolution, say, but you would be verifying by computing truth tables. Because computing truth tables, it always takes exponential time, but resolution not always, right? So therefore, you would not be able to bound the time with an just by constant. Right. So that's the point. For which proof techniques can you write this theorem? So definitely you can do it also for truth tables, right? If the time you take constructing the truth table is t, then definitely you can, it's going to take O of t, right? But that's useless because using the truth table is not a good verification technique. It has to be something that is accepted by the community as making sense, right? As being reasonably efficient, at least in some cases, right? Yeah. Okay, thank you very much.
Long live India and France friendship.